So we are at the final stage of this tour, and hopefully you enjoyed the impact of Schumacher-Levy on Jupiter. Yeah, and as I said, better him than us, because you can imagine what damage this would have done on Earth. So next time you see somewhere Jupiter in the night sky, say a thank you, because I'm pretty sure he hoovered a lot of these bigger dangerous comets away. Okay, then let's continue. Another interesting part of the solar system is the Kuiper Belt. So, about 30 to 50 astronomical units, so Neptune's orbit 30 astronomical units, and they're going out, compromising of a lot of objects. So before Gaia we knew about 2000, and now with Gaia mapping the sky we know about more than 10,000 of these Kuiper Belt objects. So it's estimated that there are about 100,000 that are larger than 100 kilometers in diameter, and of course much more that are smaller. Well, it also contains then quite some dwarf planets like Eris, Makey, Aurora. I'm not a good Hawaiian. So, and it's of course another source of comets. And how was it made? Well, again, very likely while the planets formed inside, where we had loads of material. Outside there, simply the cloud was not dense enough to form a bigger body. But nevertheless, there is now this large number of smaller bodies. And what are they made of? Well, we're gonna see. So in total, the shape of it is a bit of donut-like. And interestingly, it's slightly twisted to 7 or 8 degrees relative towards the plane of the planets. Oops. Why? One theory is that at the very beginning of the very early solar system, that their star was passing by. A smaller star at a distance less than a few hundred of astronomical units, and this then twisted everything. So the material that is easy to follow, the lighter one, is then twisted. Well, obviously it's hard to observe such smaller objects, very faint ones. And to visit it, of course, we also need a special, almost one needs to dedicate a probe, but then also what happened basically a couple of years ago, there was this New Horizons mission, also satellite. It was sent to Pluto to investigate Pluto. But once they were there, they had a bit of fuel left. And then they thought, why not use this to direct our probe to fly by closely on one of these Kuiper Belt objects. Then it was investigated also with optical telescopes, trying to find out how big it is and so on. So they picked out one that was to be easily to be reached, with not too much fuel left in order when the flyby and Pluto ends. But basically the probe goes out. Oh, and this is left side is the photograph that it took. So basically this peanut shaped stuff. So if you buy peanuts, the original not already peeled but still in the shell. And this looks quite similar. Well, here's a picture of a comet made by another probe, Rosetta, which was investigating comets or going to a comet. Looks quite similar, and basically this looks to me like a snowman that has been twisted. So basically two balls, snowballs that have been stuck into each other, and then we get darker and brighter spots. So of course dirtier and less dirtier snow. So hopefully next winter there will be opportunity again, and you can build your own Kuiper Belt object. Of course, then people immediately, to give you a feeling, this here are 5 miles. So what will this be in total? 20 miles long. Oh, and then if one takes a look, this looks a bit like when you have start with a small snowball, then you grab another handful of snow and attach it, and then it grows with time. This object was first named Ultima Thule, but then somebody was smart enough to look up Ultima Thule, which is some from the Viking mythology, some place that is really, really cold. But then somebody Googled it and found out this was a project by the Nazis. And then of course everything that has been touched by the Nazis, they have somehow the inverse gift of King Midas. What they touched was then afterwards spoiled. So one got another name, which was then this Arokoth, which is from the Algonquin language. I think this is a bigger group of Native American tribes in the Canadian area. So the Hurons belonged, I think, to them. And in their language it means basically sky. Okay, so I managed to say that, to avoid to say that Ultima Thule was the secret basis on the South Pole. Sorry. Of course there is no such thing as a secret base on the South Pole. Everybody knows this. Okay, so we are now relatively far out. We have basically from the objects that still form some structure. I would say it's the Kuiper Belt. Oort cloud is just a randomly accumulation. We have seen beforehand this Eris that goes quite out and beyond the Kuiper Belt. But I think it was 2003, an object was discovered which was called Sedna. Sedna is from the Inuit, so the goddess of the sea. And this is obviously somewhere a place where one doesn't want to take a bath in the sea. Here is the original photograph from this Palomar Observatory, which I think is the observatory where Edwin Hubble worked for. And then somebody took really great care and found here this little spot. Obviously there are lots of spots, but must be a meticulous character. And then he did what is quite reasonable. He tracked out older photographs and checked. So whether there is this spot also somewhere nearby, and then one can work out an orbit and yeah, one seen. So it was then also recognized in older photographs. And then what's realized that this is an orbit, and it has an orbital period of 11,400 years. Exactly. And now you use Kepler's law, third law. You remember the cube of the period is proportional to the square of the period is proportional to the cube of the radii. The distance to of the orbit. And then you set 1 year and 1 astronomical unit proportional to 11,400 years and the distance. But how big is this object basically that makes such a spot? Of course, to make such a spot is also this called also the albedo of objects. How much do they reflect in light? Of course, you can have a big object, but it's dark, or it's full of dirt, dark or black. It will rather absorb and not reflect. If it's full of ice, ice would reflect a lot. So also this leads then of course to, even when you know how far it is away, and because you observe the parallax, you you observe how much light is coming back. You still don't know about this albedo. This gives you, of course, uncertainty in the extension of the object. Nevertheless, we can for Sedna, we can nail it down to be 800 to 1100 miles in diameter. So, oh, 1700 kilometers for me as continental. Sorry, I still struggle a bit with miles. Oh, in comparison, other dwarf planets, Quora, my God. Sorry for my terrible spelling. If there's somebody from Hawaii, please don't beat me up for this. Then there's Pluto, a bit taller but smaller than our moon. Just half the size of our moon. Oh, this is about the size of the planet, and seemingly it has from the albedo, so it's rather a bit darker body. Whether it's really reddish, I doubt that we can see this. Okay, but now it's a lot of suspense is growing. How far is this stuff going away? Obviously, at the moment when we observed it, it's not that far away. So if we take the Kuiper Belt, and it's maybe 100 to 150 astronomical units away. At its point of closest approach, it will be 76 astronomical units. So 2076, it's basically a halo event. And then it flies away. And its farthest point will be about 1000 astronomical units away. Since it's still bound to the Sun, I would say this is a solar system object. This would make, of course, if we define our solar system, where do we end it? Where do we end our solar system? Then it would be quite big. 1000 astronomical units. Or 8 light minutes multiplied with 1000, this means 8 minutes with 1000, 80,000 minutes divided by 60, 1000 hours. This means about 6 to 7 light weeks. So light basically produced here until it comes to the end, 6 to 7 weeks. Oh. So the inner solar system is with Pluto included. So this 30 to 50 light years, this Kuiper Belt 50 light years, and Pluto, this difference between 30 at closest and 50 in furthest approach. And then we go back to Sedna makes our solar system very big. And possibly there are bodies that are even further away but are still bound by gravity towards our sun. What leads us, of course, to the question, which is the final one for today: how big is our solar system? So, do we say the last planet? But I would say the stuff is still extending out. And then we have seen the solar wind. There's then what is called the termination shock, the heliopause, or the hydrogen wall. And our one of the Voyager has just made it out of this termination shock. Drastically decrease in this in the hydrogen. So obviously there is still a bit more hydrogen than towards the interstellar medium. And since our sun is moving, don't forget, inside the galaxy, and our galaxy is moving, but I would say the relative movement inside our galaxy is the decisive one to pick up more dust. This leads then here to this bow shock. And so we still have outside a bit of this heliosphere, this a bit of the solar wind, but then relative to the other dust, it's a bit compressed at the front but longer at the back. So what is the size of our solar system? Neptune's orbit, 30 astronomical units. Kuiper Belt, 50 astronomical units, would also include Pluto, this hydrogen wall, about 200 astronomical units. So, Sedna's orbit, 1000 astronomical units, then we would be already quite big. Or do we say that all territory between our sun and its nearest neighbor? Again, we have two stars. So nearest neighbor, let's say it's Alpha Centauri. Other people would say this is Proxima Centauri. So they're roughly this 5.76 light years away. Then we can now define if they are similar size, or we can define anyway what is called this Lagrangian point 1. If you have two bodies, so stop sharing, that's enough for anyway for today with the slides. So if you have two bodies, here, and you put another body in between. Depending on the mass, if you have here a big one and here's a small one, or big one, small one. We shift now this mass in the middle between. There will be one point where the gravity to the big body is equal as the gravity to the small body. So no gravity at all. This is this Lagrangian point 1, if you remember. If we define this, then our solar system would be 3 light years across. In one direction would mean 6 light years in diameter. So, something to discuss. I don't know, probably with fun checks in the Oxford dictionary or somewhere there is certainly a definition given. Some guys met in a fancy hotel, trip paid, discussed what take it and then made a definition. I should look it up. Okay, otherwise you can look it up and tell me. That's it for this week. So the gross structure of our solar system and a few points towards the planet. And next week we look a bit more about the structure of the planets and the atmosphere of the planets, whether there is possibly some life, and then we go a beyond our solar system. But there are 2 or 3 places in our solar system where possibly even life could exist or evolve. And if we go beyond, let's see. So how do we find first the methods? How do we look for exoplanets? What do we have found so far? How good is it? Can we resettle? It's also, we've learned in this module that basically the sun at some point, so probably 1.5 billion years, is becoming so hot because this it slightly already burns more carbon, or slightly carbon. Therefore the CNO cycle becomes more. The CNO cycle is much more effective to burn the hydrogen off, produces a bit more energy, and already becomes hotter. In probably 1.5 billion years it's so hot that where the Earth is, it becomes too warm to have liquid water. We don't want to live then anymore. 1.5 billion years. Clock is ticking. Well, it's still 1.5 billion years. And if you look at it in an hour, it's 1.5 billion years. If you look next year, it's 1.5 billion years. So, okay, with this, I hope you enjoyed this lecture. See you then for the tutorial session. Bye.